As we gaze into the vast night sky, a profound sense of wonder and curiosity envelopes us. Are we truly alone in this expansive universe? Is there another planet, akin to our Earth, teeming with life and awaiting discovery? The quest for what scientists and dreamers alike call Earth 2.0 has sparked a renaissance in astronomical research, driving us to explore the cosmos for worlds that may harbor life. This pursuit not only fuels our imagination, but also deepens our understanding of the delicate balance required for life to thrive. To embark on this monumental journey, we must first define the key characteristics that contribute to a planet's potential habitability. Identifying these characteristics is crucial, as the conditions necessary for life are complex and nuanced. A planet must not only possess the right physical attributes, but also a range of environmental factors that create a hospitable setting for biological systems. The criteria for habitability may be more intricate than we ever imagined, and our search may lead us to rethink the very nature of life itself. At the forefront of our exploration is the concept of the habitable zone, commonly known as the Goldilocks zone. This is the region around a star where conditions are just right, not too hot and not too cold, for liquid water to exist on a planet's surface. The presence of liquid water is a hallmark of habitability. It is essential for life as we know it. As we identify potential candidates for Earth 2.0, we pay close attention to their distance from their parent stars. Too close and water will boil away. Too far and it will freeze. Finding that sweet spot is a critical step in our search for life. Liquid water is more than just a necessary component. It is the lifeblood of any potential ecosystem. Water acts as a solvent for biochemical reactions, facilitates nutrient transport, and plays a crucial role in regulating temperature and climate. Thus, scientists actively seek planets with significant bodies of water, whether in the form of vast oceans, smaller lakes, or even icy surfaces. Each form of water can provide different opportunities for life to emerge. Understanding how water exists and circulates on these distant worlds is vital to assessing their habitability. Next, we turn our attention to the atmosphere of a planet, an essential component in determining its potential for life. A thick and stable atmosphere serves multiple purposes. It regulates temperature, protects the surface from harmful solar radiation, and maintains the pressure necessary for liquid water to exist. The composition of this atmosphere is equally important. It must contain gases that can support life processes. An atmosphere rich in oxygen, nitrogen, and carbon dioxide could facilitate biological activity, while extreme or toxic compositions might render a planet inhospitable. The balance of these gases is a delicate dance that could signal the presence of life or its absence. Geological activity is another cornerstone in maintaining a habitable environment. A dynamic planet, characterized by tectonic movement, can recycle crucial elements and sustain a stable climate over geological timescales. For instance, volcanic activity can enrich the atmosphere with essential gases, while the movement of tectonic plates regulates carbon cycles, helping to stabilize temperatures. This geological dynamism creates a rich tapestry of environments that foster adaptability and resilience in life. Understanding the geological history of a planet can provide insights into its past and future habitability. A planet's magnetic field is yet another critical factor in the search for habitability. This invisible shield protects the atmosphere from being stripped away by solar winds and guards the surface from harmful cosmic radiation. Earth's magnetic field is a vital reason our atmosphere remains stable and conducive to life. Without it, the potential for life on a planet would dramatically diminish. The presence of a magnetic field, therefore, adds another layer to our assessment of a planet's potential for supporting life. The search for habitable exoplanets has gained unprecedented momentum in recent years, fueled by advancements in technology and innovative observation techniques. Missions like NASA's Kepler and the Transiting Exoplanet Survey satellite, TESS, have identified thousands of exoplanets, some of which lie within their stars' habitable zones. Researchers meticulously analyze data from these missions to assess whether these distant worlds possess the right conditions for life. Each discovery brings us closer to identifying planets that could potentially be our next home. However, locating a planet within the habitable zone is merely the first step. Scientists are also keenly focused on identifying biosignatures, indicators of life, such as specific atmospheric gases that might suggest biological processes are occurring. For example, the simultaneous presence of oxygen and methane in an atmosphere could signal ongoing biological activity, as these gases tend to react chemically and would not typically coexist without a continuous source. The quest for biosignatures transforms our search from merely locating planets to understanding their potential for supporting life. To explore the environments of these exoplanets, researchers conduct simulations that mimic the conditions found on various planetary bodies. By recreating extreme environments in laboratory settings, scientists can test the resilience of potential life forms and explore how life might adapt to diverse planetary conditions. These experiments not only broaden our understanding of biology, but also refine our expectations of where and how life could arise in the universe. As we search for Earth 2.0, we must also take a moment to reflect on the unique conditions that make our home planet so special. Earth's extraordinary biodiversity, its climate stability, and its geological activity create a rich and diverse environment that we are only beginning to understand. The lessons learned from studying Earth are invaluable. They guide our exploration of distant worlds and enhance our understanding of what is truly required to sustain life. The search for habitable planets extends far beyond mere curiosity. It invites us to contemplate our own place in the universe and emphasizes the importance of preserving our planet. As we look outward into the cosmos, we must also look inward, recognizing that the survival of life on Earth is intrinsically linked to our exploration of other worlds. Our quest for knowledge is not solely about finding new homes. It is about understanding and nurturing the one we already inhabit. Moreover, the quest for Earth 2.0 unites scientists from around the globe, transcending cultural and national boundaries. This collaboration fosters innovation and inspires future generations of researchers and explorers. The diversity of thought and perspective enhances our understanding of the universe and enriches the scientific community. By working together, we can accelerate discoveries and forge a deeper connection with the cosmos. As we continue this journey into the stars, the question remains: where is Earth 2.0? Each new discovery offers a glimpse into the possibility of life beyond our planet and challenges us to reconsider our understanding of what it means to be habitable. With each leap forward in technology and knowledge, we move closer to answering one of humanity's oldest questions: are we alone in this universe? The quest for Earth 2.0 is not just about finding another home. It is a journey filled with promise, potential, and profound implications for our understanding of life itself. As we unravel the mysteries of the universe, we not only seek to discover new worlds, but also to deepen our appreciation for the fragile and precious existence we share on our own planet.